Alright, what's up guys? In this video I'm going to play with some calculus and we're going to be talking about surface area. So we're asked to find the surface area of a solid, which is obtained by rotating the given parametric curve about the x-axis. So they give us these parametric equations here. X is equal to cosine cubed theta and y is equal to sine cubed theta, where theta is between 0 and pi over 2. So there are two surface area formulas, and they differ depending on the axis in which you're rotating. So let me specify those. So if you're rotating about the x-axis, then the surface area will be S is equal to the integral 2 pi y ds, and I'll specify what ds means. So this is when you're rotating about the x-axis. So that's the first formula for the surface area. Now the second formula, if you're rotating about the y-axis, then it's going to be the integral 2 pi x ds, and again this is if you're rotating about the y-axis. Now this is very important because you have to look at what axis that you're being rotated over, because you can't just use any one of these surface area formulas you want. You have to check the axis that you're dealing with. That way you can avoid getting the wrong answer. So this is rotation about the y-axis. And the last part is the ds part. So if you remember in the videos that we do on line integrals and stuff like that, remember the ds part from that, hopefully you remember, depending on whether it was R2 or R3 if we were dealing with a line integral. Remember, it'd just be the square root of, in our particular case, it'll be theta since we're dealing with theta, so it'll be dx over d theta squared, or the square root of dx over d theta squared, plus the square root, or plus dy over d theta squared, and d theta. So that's all ds is. Okay? So as you can see here, there's not really much to do other than we can go ahead and take our derivatives, and then we deal with that messy square root, and we got to integrate, and that's pretty much the goal here. So let's take the derivatives first. So we need dx over d theta. So that means that we need to differentiate cosine cubed of theta. Okay, so to differentiate that, we use what's called the chain rule for powers. And in that case, we'll get minus 3 cosine squared theta multiplied by sine theta. That's just chain rule. And then we need to find dy over d theta. Same thing here. We want to take the derivative of sine cubed theta. Again, just use the chain rule for powers, and that just becomes 3 sine squared theta multiplied by the derivative of sine, which is cosine, so that'll be cosine theta. Okay, so make sure you're good with that derivative taking stuff. That way that doesn't cause too much of an issue for you. And then at that point, all we gotta do is really set it up. Now, 2 is a constant, and pi is also a constant. Remember, pi is just a number, so it's a constant. It's like 3.14. I don't even remember the rest of the numbers, but it's just a constant. So just pull it out, and then we'll have our integral. We know the limits of integration are gonna be from 0 to pi over 2. Now we're gonna do the simplification and stuff with the square root in a few minutes. I'm just kind of setting it up so that you can have a general idea of how it needs to be set up. So again, keep in mind that, well, I've been just using theta, but I put of theta there, so I'll change it a little bit. Doesn't matter if it's theta or of theta, however you want to say it is fine. But since I did it down here, I might as well be consistent and do it up there. So since we're rotating about the x-axis, we're using that formula up here at the top, which means that y was left in our integrand here, and all I did was replace y with sine cubed theta, because again, rotation about the x-axis. So this is the formula that we should be using, and not that one. So which one you use depending on the axis that you're given. And so when we plug all this information in, we get negative 3 cosine squared theta multiplied by sine theta squared. And then this would be plus 3 sine squared theta multiplied by cosine theta. And that's going to be squared. And again, we're integrating with respect to theta. Now we're going to clean all this up, but this is how it needs to be set up. Okay, so let's go ahead and begin by cleaning up that square root, because that's going to create a little bit of problems. And you want to make sure you simplify as much as possible, because if you just try to integrate that, you're not going to have a good time. So you want to do as much simplification as you can. So notice here, you got to be careful. Notice here that we're squaring the 3, we're squaring this cosine, we're squaring the sine, same thing over here. So you have to be very, very careful when we're doing the simplification here. So this will give us 9 cosine to the 4th theta, or of theta. So I did of theta earlier, so let me change it to of theta. Again, it doesn't matter, but I'm just trying to be consistent. Then this would be sine squared theta. And then this would be plus 9 sine to the 4th of theta multiplied by cosine squared of theta d theta. So just taking care of the ds part. Now we can break this square root up a little bit, because we know that cosine squared theta plus sine squared theta is equal to 1. So I can break this up as the square root of 9 sine, sorry, not 9 sine, 9 cosine theta sine theta times the square root of cosine squared theta, or of theta, plus sine squared of theta. Should have probably just stuck to theta because I keep forgetting to write of theta. So after we do the simplification, this is what ds will end up being. It will end up being 3 cosine theta, cosine of theta times sine of theta. Again, this is just 1. The square root of 1 is 1. So I'd be multiplying 1 by this, which is just all that. And so that would be the ds part. So what we've done is, when we get another sheet here, we've done the simplification, and that has worked out well for us. So we get 3 cosine of theta sine of theta. And so you always want to do as much simplification as possible. This happens a lot with the arc length integrals, because, you know, obviously we got square roots in those too. And some arc length integrals can just flat out be a nightmare in certain circumstances, because that square root can cause some problems. So that's why, you know, it's always important to simplify as much as possible. You know, you get that messy square root out of there. So this particular case, we got lucky, and, you know, but I have done plenty of arc length integrals where that daggone square root is just causing a bunch of problems. Okay, so now that we've done the simplification, if you remember, when we go back, we had pulled out the 2 pi. But if you remember here, when we got our ds, we got 3 cosine of theta sine of theta. Well, 3 is also a constant and can be pulled out as well. And so then we'll have the integral from 0 to pi over 2. Okay. Now, notice that when we go back to our integral, we actually set the problem up. We already had a sine cubed in there. So we would have sine cubed times another sine, or sine cubed of theta times another sine of theta, which would give us sine to the 4th of theta. But we also have a cosine in there, or multiplying by cosine as well. So this essentially just becomes sine to the 4th of theta multiplied by cosine of theta integrated with respect to theta. All right, so hopefully you're still with me on all this. So we just got to integrate this now. And this is a pretty easy integral to do. So just a u substitution is all that's really needed. We can easily pick u in this particular case to be sine, because the derivative of sine is right there in the integral itself. And if the derivative of it is in the integrand, the derivative of whatever your u is, you know that you're making a good that you've chosen the correct method. It doesn't always have to be exactly the same, and it's not always going to be exactly the same, but being close enough is enough to get something to cancel out. It's fine to do a substitution. So du will be cosine, again, of theta. There I go again. So it'll be of theta, d theta. So we'll get 1 over cosine of theta du is equal to d theta if we solve for the d theta part. And so hopefully what you'll see is that the cosines will cancel out. And since we pick u to be sine of theta, well, then that means that'll be u to the 4th. Now we can do the simplification of the constants on the outside. Well, 2 pi times 3 is 6 pi. And then we'll have our integral. We'll have to change the limits of integration. This would be u to the 4th du. Now we change the limits, so remember that u was equal to sine of theta. So to change them, we just plug in. So we get sine of 0. Well, sine of 0 is 0. So ugly looking 0, sorry. And then we need sine of pi over 2. Sine of pi over 2 is 1. So now it'll be from 0 to 1. So let's go down here actually. So we got 6 pi, the integral from 0 to 1. And it's going to be u to the 4th du. And we go ahead and do it. So 6 pi is just a constant. We apply the power rule. We get u to the 5th over 5 evaluated from 0 to 1. So we know that this is just going to lead us with 6 pi multiplied by 1/5, which will give us 6 pi over 5, which we can't reduce that any further. And that would be the answer, and that would be your surface area. So your final answer for this particular problem, our surface area, which we denoted S. So surface area is just going to be that. It's going to be 6 pi over 5. That's your answer. All right, well, I hope that made sense. I hope everything is making sense. I try to be as thorough as possible, and I try to, in my videos, give very, very good explanations for why we're doing what we're doing. Because in math, it's not just good enough to know the answer. It's good to know how to get the answer and why we do what we do to get the answer in the first place. Just knowing the answer isn't going to get you very far. I mean, I guess it's okay for some people. Again, you really need to know the reasoning behind why we do this stuff. Why do we do integration by parts for this integral versus a trig substitution? Why do we do u substitution versus partial fractions? Those sorts of things. So I like to expand on my explanation of what's actually being done. Okay, so that's going to be it for this video. I'm going to post some more content for you guys to see. So reach out to me if you got any questions. We'll see you next time.